Hi everyone. Today we're going to study tautology, contradiction, and contingency. Let's begin with a definition of tautology. Tautology is a compound proposition that is always true, no matter what truth values of the propositions that occur in it. Let's see this example. Prove that P or not P is a tautology. Let us write the column for P, and the possible truth values are true and false. For not P, we negate the values of P. T becomes F, F becomes T. Now, P or not P. Remember that the OR operation is always true for at least one true in the propositions involved. So T or F is T. F or T is T. Since all truth values here are true, P or not P is a tautology. This is our final answer. Let us now define contradiction. Contradiction is a compound proposition that is always false. Let's see this example. Prove that P and not P is a contradiction. The column for P with the values true or false are here. Not P, we negate all the values of P. T becomes F and F becomes T. Now, P and not P. Remember that the AND operation is only be true if both propositions are true. So here, the T and F is F. F and T is F. Since all values in this column are false, P and not P is a contradiction. This is our final answer. Let's define contingency. Contingency is a compound proposition that is neither true nor false. Let's see this example. Prove that not P and not Q is a contingency. We write the columns P and Q, and we write here all the possible combinations of P and Q. For the column P, we write T, T, F, F. For the column Q, T, F, T, F. Now, we write the negation of P and the negation of Q. Here are now the corresponding truth values. Let us now evaluate not P and not Q. Remember that for the AND operation, it is only be true if both propositions are true. So we have F and F is F. F and T is F. T and F is F. T and T is T. We can see here that truth values are neither all true nor all false. It is combination of true and false here. So not P and not Q is a contingency. This is our final answer. Today, we're going to study logical equivalence. Let us define logical equivalence. The compound propositions P and Q are called logically equivalent if the biconditional proposition P, if and only if Q, is a tautology. We use the symbol like this, and this is read as P is equivalence to Q, or P is logically equivalent to Q. Let us see this example 1. Show that P implies Q is logically equivalent to not P or Q. For our solution, let's begin with writing the tables for the values of P and Q respectively. And then, let us first evaluate the right side of this equivalence. Let's begin with the negation of P. So not P is here with the corresponding values for T becomes F and F becomes T respectively. Now, let's have not P or Q. Remember that for the OR operation, this is only false when both of the propositions are false. So the values are F or T is T, F or F is F, T or T is T, T or F is T. Next, the P implies Q. So the values are T and T is T, T and F is F, F and T is T, F and F is T. Remember that for the implication, this is only false when P is T and Q is false. Now, let us consider this column, not P or Q, and the column P implies Q. We can see that they have the same truth values everywhere. So we write, since P implies Q is true whenever not P or Q is true, and P implies Q is false whenever not P or Q is false. Therefore, P implies Q is logically equivalent to not P or Q. This is our final answer. Example 2. Verify that the negation of the compound proposition P or Q is logically equivalent to not P and not Q. Let's begin with writing our table for P and Q with the corresponding truth values. Then, let us evaluate P or Q. And here are the corresponding truth values. T or T is T, T or F is T, F or T is T, F is F. Next, we will negate this column. So T here becomes F and F becomes T respectively. And then, let's have the negation of P and negation of Q. So all the values of P and Q are negated on these two columns. And then, let's have not P and not Q. So we have F and F is F, F and T is F, T and F is F, T and T is T. From here, let us compare these two columns. We can see that they have the same truth values everywhere. So we say that since the negation of the compound proposition P or Q is true whenever not P and not Q is true, and the negation of the compound proposition P or Q is false whenever not P and not Q is false. Therefore, the negation of the compound proposition P or Q is logically equivalent to not P and not Q. This logical equivalence here is part A of De Morgan's law for propositions, while the part B is here, the negation of the compound proposition P and Q is logically equivalent to not P or not Q. We're going to leave this part B of De Morgan's law for practice for students. Let's have example 3. Show that P or the compound proposition Q and R is equivalent to the compound proposition P or Q and the compound proposition P or R. We can see here that we have three propositions P, Q, R. So let us start with the truth values of P, Q, R respectively. And then let us evaluate Q and R. And the values are here. Next, let us evaluate P or this Q and R. This is our P and this is now the Q and R. Let us connect them with the operation OR. The values now are here. And then let us now evaluate P or Q. And the values are here. Next, let us have the P or R. And the values are coming now in here. And then let us have this P or R and the compound proposition P or R. So we will connect these two columns with the operation AND. And the values now are here. Let us compare this column with this column. We can see that the truth values are the same correspondingly. So we say that since P or the compound proposition Q and R is true whenever P or Q and the compound proposition P or R is true, and P or the compound proposition Q and R is false whenever P or Q and the compound proposition P or R is false. Therefore, P or the compound proposition Q and R is logically equivalent to the compound proposition P or Q and P or R. Take note that what we prove here is the part A of distributive laws, and the part B of distributive laws is here, P and the compound proposition Q or R is logically equivalent to compound proposition P and Q or the compound proposition P and R. We're going to leave this part B for students to prove. Today, we're going to study properties of logical equivalence. Let us do a short review. Two logical statements are logically equivalent if they always produce the same truth value. Consequently, P is logically equivalent to Q is same as saying P if and only if Q is a tautology. Here are now properties of logical equivalence. For any propositional variables P, Q, and R, and truth values T for true and F for false, here are some important properties of logical equivalence. Number 1 is identity loss. We have two parts. 1a, P and true is logically equivalent to P. 1.b, P or F is logically equivalent to P. Second, domination loss. We have two parts here. 2.a, P or T is logically equivalent to T. 2.b, P and F is logically equivalent to F. Third is idempotent loss. We have two parts also. 3.a, P or P is logically equivalent to P. 3.b, P and P is logically equivalent to P. Number 4, double negation law. This is the negation of not P is logically equivalent to P. Number 5, commutative loss. We have two parts. First part, 5.a, P or Q is logically equivalent to Q or P. 5.b, P and Q is logically equivalent to Q and P. Number 6, associative loss. We have two parts also. 6.a, P or the compound proposition Q or R is logically equivalent to the compound proposition P or Q or R. 6.b, P and the compound proposition Q and R is logically equivalent to the compound proposition P and Q and R. Number 7, distribution laws. We have two parts. 7.a, P or the compound proposition Q and R is logically equivalent to the compound proposition P or Q and the compound proposition P or R. 7.b, P and the compound proposition Q or R is logically equivalent to P and Q or the compound proposition P and R. Number 8 is De Morgan's laws. Here are the two parts. 8.a, the negation of the compound proposition P or Q is logically equivalent to not P and not Q. 8.b, the negation of the compound proposition P and Q is logically equivalent to not P or not Q. Number 9 is absorption loss. We have two parts. 9.a, P or the compound proposition P and Q is logically equivalent to P. 9.b, p, and the compound proposition p or q is logically equivalent to p. Number 10 is negation laws. We have two parts. 10.a, p or not p is logically equivalent to t or true. 10.b, p and not p is logically equivalent to f or false. Number 11 is equivalence of an implication and its contrapositive. So this is p implies q is logically equivalent to not q implies not p. Number 12, writing an implication as a disjunction. P implies q is logically equivalent to not p or q. Number 13, negation of an implication. The negation of the compound proposition P implies Q is logically equivalent to P and not Q. I hope you learned something from this video. See you again next time.